Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be covering rate equations, sometimes called rate expressions. We're going to look at the importance of these, what the different components of the expressions are, and how we can work out those different components one by one. Firstly though, have a go at this question, describing the way to find the initial rate of reaction. So hopefully you remembered that to find the initial rate of reaction, we have to find the gradient of a tangent to the concentration time curve at time equals 0. So the rate equation basically allows us to calculate the rate at a given concentration of reactants without actually doing the experiment. And it also allows us to see the relationship between the different reactants and the rate of reaction. So for a reaction like A plus B goes to C to D, the rate equation would read like rate is equal to K times the concentration of A taken to the power of the order of A times the concentration of B taken to the power of the order of B. Now, it's important to understand here the order has nothing to do with the stoichiometric coefficients of the overall equation. We are unable to determine the rate equation from the overall equation. It's a very common mistake, so you will need to use the techniques we're going to look at in this video to be able to determine the different orders. Now, I'm going to go through what we really mean by order, how we can determine it, and what it represents in a few moments. But first, we're going to have a look at that term K, or the rate constant. So K is effectively a measure of how readily a reaction takes place, and therefore how high the rate is. Higher values of K indicate a higher rate of reaction, and lower values of K indicate a lower rate of reaction. So potentially counterintuitively, however, K is dependent on temperature. So although we call it a constant, it's actually only constant at a given temperature. So as temperature increases, the value of K will obviously increase because we increase the kinetic energy of the particles. And as temperature decreases, K will therefore decrease. Where K stays true to its name as a constant is in relation to the concentration. It is independent of the concentration of the reactants as long as the temperature is fixed. The next component is the reaction order, this thing we take the reactant to the power of. And so this describes how changes in the concentration of a reactant affect the overall rate of reaction. Of course, assuming that temperature and pressure are fixed. At IB, we're only going to cover 3 different scenarios for this. First is called 0 or 0th order, and we'll cover 1st and 2nd order in a moment. So for 0 order, we have A to the power 0. Now anything to the power 0 is of course 1, so anything that is 0th order will not actually appear in the rate equation. And if it doesn't appear in the rate equation, then changing it does not affect the rate. So 0 order reactants do not affect the rate of reaction. For example, if we double the concentration of A to the power 0, then we have the same rate that we started with. When we look at reactants that are 1st order, that's A to the power 1, will result in changes of rate of reaction that are directly proportional to the changes in concentration. E.g., if we double the concentration of A, then we're going to double the rate of reaction. And when it comes to 2nd order reactants, you guessed it, that's A to the power 2, any change that we make in the concentration of A is going to lead to a change in rate that is equal to that change squared. So we could say the rate is proportional to A squared. For example, if we double A, then we would quadruple the rate of reaction. So now we can properly interpret a rate equation and maybe understand what it might be expressing to us. we want to be able to determine the order of the reactants, and we're going to use 3 different methods to do this: concentration time graphs and half-life, rate concentration graphs, and inspection of initial rate data. But first, concentration time graphs. These are the same graphs that we were using previously in our rate calculations. So let's have a look at concentration time graphs when we've got 0th, 1st, and 2nd order reactants. Well, with 0th order reactants, we know that changing the concentration will not change the rate of reaction. So we expect a linear gradient downwards. For 1st order reactants, we know that the change is directly proportional to the concentration, so we're going to see this downward, evenly curved slope. For 2nd order reactants, we know that it's going to be A squared, so we're actually going to see this graph that looks like a 1 over x kind of graph. So what do these graphs show us? Well, for 0th order, they show us that the rate does not depend on the concentration of A, because as the concentration decreases, the rate of reaction is staying the same. So the rate will remain unchanged even as we see a steady fall in the concentration of A. In the 1st order graph, we see that the rate is dependent on A, and it's directly proportional to A. We can see this because as we decrease the concentration of A, we also decrease the gradient of the line and decrease the rate of reaction. So because we've got a decreasing rate of reaction, it must be dependent on the concentration of A. In the 2nd order reactant, we see that the rate is proportional to A squared. So as the concentration of A falls, the rate also falls. However, this decline in rate will be slower than that of a 1st order reactant. Now, sometimes with data, it may not be so obvious if we have a 1st order or a 2nd order reaction. And that may be based on the range that we choose for our increments, which is why we should always do preliminary experiments. But nevertheless, we can kind of double check or use what's called a half-life to determine the order of reaction. So a half-life is the length of time that it takes for half of the concentration of a reaction to be used up and turned into products. And the key point here is that only 1st order reactions have a constant half-life, where that time it takes to use up half of the reactants is the same. Let's take a look at the graphs we've already drawn. So if we keep taking half-lives on this 0 order reaction, you'll see that over time, the half-life decreases. The time it takes to remove half of the concentration decreases over time as we have that negative slope. As I've already said, if we do the same for the 1st order reaction, we see that the time that it takes for the half-life to occur stays consistent. And so that constant half-life is the marker of a 1st order reaction. For the 2nd order, we can see that the half-life is going to increase over time. So that's a way we can use the half-life to determine the order of reaction. These all actually have equations that we can use for the half-life as well, for both 0, 1st, and 2nd order. We use 1 over K times the concentration. Our next option is to use rate concentration graphs. Here we are plotting the concentration on the x-axis and the rate on the y-axis. So for a given reaction, what we would need to do is we would need to collect data for the initial rate of reaction at different concentrations of the reactants. So we set up different runs or experiments with those different concentrations, and then we plot the different initial rates of reaction at those different conditions against the concentration. So we end up with initial rate over concentration. So now if we think about a zero order reactant, we know that rate does not change with concentration. So we're going to have a flat line with a gradient of 0. In first order, we have a directly proportional upward gradient. And in second order, we're going to have an upwards trending curve. And this obviously relates to how these reactants change the rate. So if the reaction is zero order, it does not appear in the rate expression, and the y-intercept in that case is equal to the rate constant. So where the line meets the y-axis tells us the rate constant for a zero order reaction. Now for a first order reaction, as we said, we've got a directly proportional relationship. So here the rate is equal to K times the concentration of A, and because of that, if we take the gradient of the line, then the gradient of this line is equal to the rate constant K. Now, with second order reactions, the rate is obviously equal to K times A squared, and so it's proportional to A squared. Now, we can't find the rate constant directly from this graph. We would need to make the graph of 1 over A squared, and then that would give us a straight line. And we could actually take the gradient of the line of that graph, and that would give us the rate constant. So that kind of covers the first two of the three methods. Now we're going to have a look at inspecting initial rate data, and this is a very common exam type question at IB. So let's have a look at some data. So really, we've got experiments, concentrations, and we've got the rate. So we've done different experiments with different concentrations. This is assuming temperature stays the same. And then we're going to go through and determine what is the order of reaction with respect to A, B, and C. And then we're going to write the rate expression from that. So let's first look at A. We need to find two experiments where first B and C stay the same and A changes. In this case, experiment 1 and 2 offer a perfect example where the concentration of A is doubled. Now, when we look at the concentration of A, we also want to look at how the rate changes. So what we do is we do the large value divided by the small value, and we see that we have a factor of 2 change, which means the factor of change is the same as the factor of change in concentration. So the reaction must be first order with respect to A. Now we can do the same process with B. We want to find a place where B changes and A and C stay the same, which in this case is experiment 2 and 3. We see a doubling of the concentration causes a factor of 4 change. So that is 2 squared. So the reaction must be second order with respect to B. Lastly, we're going to look for C, and we're going to find the same thing again. We want to find where C changes and the other two reactants remain the same. So 1 and 4 work well for this. Now here we're doubling the concentration of C and the reaction rate remains the same. So the reaction must be 0th order with respect to C. So the overall rate expression must be rate equals K times A times B squared. And the overall order of the reaction is 3, or third order. Now, before we go about rearranging this equation to actually find the value of K, we want to make sure that when we're trying to find a value of K, we know what units K is going to be in. And that depends on the overall reaction order. So for a 0 order reaction, rate is going to be equal to K. And so therefore the units of K will be the same as rate, which will be moles per decimeter per second. However, once we start looking at the other reaction orders, we have to be a little bit more careful. First order reaction is going to be K times A. So we're going to have moles per decimeter per second divided by moles per decimeter. So what we can do is we can cancel our units just like we would in any mathematical equation. So we're going to find moles cancel with moles, decimeters with decimeters, leaving us only seconds to the -1 for a first order. In the case of a second order reaction, we of course have rate equals K times A squared. So that means the expression for K is going to be moles per decimeter per second over moles per decimeter squared, all squared. Now we can expand the all squared brackets to give us mole squared decimeters to the -6, and then go about cancelling using our indices. So moles divided by moles squared is going to be moles to the -1. Decimeter to the -3 divided by decimeter to the -6 is going to be decimeter to the power 3, and still seconds to the -1 by itself. So we can see the units are changing as the overall reaction order changes. The last one we're going to look at IB is third order. So this is going to be rate equals Ka cubed. It could be multiple different reactants, but for the units, that doesn't matter to us. So K is going to be moles per decimeter per second divided by moles per decimeter to the power 3. And obviously we can expand those brackets out straight away so that we get mole to the 3 and decimeter to the -9. Once we get that, we can do what we've done in all the other examples, which is to cancel out. So moles divided by moles to the 3 is going to be moles to the -2. Decimeters to the 3 divided by decimeters to the -9 is decimeters to the 6. And of course, seconds to the -1 again. So these represent the units that will accompany a given value of the rate constant with a reaction of each of these overall reaction orders. So we can combine these last two skills and actually have a go at calculating the rate constant. So here we've got another table of experiments with initial concentrations of NO and H2 with some initial rates. So to first calculate the order with respect to hydrogen, I find experiment 1 and 2, NO stays the same and H2 doubles. I find the change in rate there is also a factor of 2, so it's first order with respect to H2. Looking at N2, I can use experiment 1 and 3. In experiment 1 and 3, H2 stays the same and NO changes by a factor of 2. So we find in this situation that the overall change is by a factor of 4. And that indicates that it is second order with respect to NO because 4 is 2 squared. So we have an overall rate expression of rate equals K H2 times NO squared. Now, if I want to find the value of K, all I have to do is rearrange that equation to give me K, and I can pick any one of the experiments and just plug in the values. So for this example, I'm just going to pick experiment 2. So I plug in 5.05 times 10 to the -6 divided by the concentration of H2 multiplied by the concentration of NO all squared. And that gives me a value of 2.53 times 10 to the -3. Bearing in mind my units, moles per decimeter per second divided by moles per decimeter all cubed, which is moles to the 3 and decimeters to the -9. Once again, using indices, moles divided by moles to the 3 is moles to the -2. Decimeters to the -3 divided by decimeters to the -9 is decimeters to the 6, and seconds to the -1. That allows us to quote the final rate constant for this reaction as 2.53 times 10 to the -1 moles to the -2, decimeters to the 6, seconds to the -1, as long as temperature remains constant. So let's do a couple of questions to review. First question, use this data to find a reaction order with respect to A. Pause the video to have a go. Pop them up! So finding for A, we look at experiment 2 and 3, and we see doubling the concentration of A has no effect on the rate of reaction, so it's 0th order with respect to A. Next question, using the same data, find the rate expression for this reaction. Pause the video. Pop 'em up! So we already know that A is 0th order, so looking at B, we see reaction 1 and 2. So here we double the concentration of B, and we also get a factor of 2 change, so it's 1st order with respect to B. So the rate expression will be rate equals K times the concentration of B. So now we have that, state the units of K and find its value. Pause the video. Pop them up. So what we have to do is rearrange the rate equation to give us K, which is rate over the concentration of B. And then we can plug in the value from any run, but I'm just going to do it from the first one, which is 1.25 times 10 to the minus 2 divided by 1.00, which is of course 1.25 times 10 to the minus 2. For the units, we've got moles per decimeter per second divided by moles per decimeter, which leaves us with just seconds. Last question then, find the rate expression using this data and use that expression to find the value of the rate constant. Pause the video and take your time with this one. Pop 'em up. Just as before, we're going to find the order with respect to hydrogen first. It's 1st order. Then we're going to find the order with respect to NO. In this case, it is 2nd order with respect to NO. That gives us our overall rate equation of rate equals K times the concentration of H2 times the concentration of NO. We can then rearrange to give K as the subject and plug in the values from an experiment. I'm going to use experiment 1, which gives us an overall value of 2.53 times 10 to the minus 3. For our units, we of course have moles per decimeter per second divided by moles cubed decimeters to the minus 9. So we cancel that through to get moles to the minus 2 decimeters to the 6 times seconds to the minus 1. So that's our 3rd way to determine the order of reaction. So there is a practical to go along with this and practical workbook questions, as well as rate expression calculation questions. Thanks again for joining me, guys. Don't forget to like, subscribe, hit the bell icon, and as always, practice makes slightly better.